Hello friends, I Dr. Mohan Verma welcome you all in this course of fundamentals of engineering physics, and today's topic is black body radiation. And in this lecture we are going to learn about how to heated body radiates, because that black body radiation it's related to radiation. So, the first question we will ask about how to heated body radiates, and second, how is radiation absorbed, the mechanism of reflection by the metal surface, and the relating absorption and emission, and black body radiation spectrum, and also the explanation of this black body radiation with the help of different laws, and finalized with the quantum theory of light by Max Planck, and then the summary. And objective of this lecture is to introduce the concept of black body and black body radiation, to impart knowledge on black body radiation spectrum, to introduce various laws to explain black body radiation curves, and to discuss about the application of black body radiation. Outcome of this lecture: this topic enable you to understand the basic concepts of black body and this black body radiation, and apply Wien's and Stefan's law to analyze radiation emitted by black body, and also explain Planck's hypothesis of energy quanta to understand this black body radiation. And the background of this topic: this is one of the phenomena that could not be adequately explained by classical physics was black body radiation. So, earlier we have listed in last lecture that there are certain phenomena like that black body radiation, photoelectric effect, Compton effect, specific heat of that. So, this is one of that, and then we know these hot objects emit EM radiation. These are our daily life experience, and if we heat a piece of metal in a flame, it begins to glow dark red at first, then perhaps white or even blue if the temperature is high enough. Very hot objects would emit a significant amount of energy to ultraviolet region of the spectrum, and people are emitters of energy on the other end of the spectrum. So, these are our daily life experience. And also we can see this higher energy by using night vision goggles. The exact spectrum depends upon the properties of material and the temperature, and this black body is an ideal object that emits all frequencies of radiation that depends only on the temperature. So, we will see the details of all these things here. Just in form of this background, I am trying to give some the terminology used in this lecture. So, the question is, how do heated body radiates? In the turn of the century 1900, the physicists have a puzzle that how do heated body radiates, and heat was known to cause the molecules and the atoms of a solid to vibrate, and these molecules or atoms were themselves a complex pattern of electrical charges. So, we know that the structure of these atoms and molecules in chemistry and physics. So, these are the atoms, and from the experiments of Hertz in the year 1887 and others, Maxwell predictions that oscillating charge emits electromagnetic radiation had been confirmed. So, in that electromagnetic wave lecture, we have discussed about the details of this experiments and its properties. And we already know that this light itself and the closely related IR heat radiates, and these were actually electromagnetic waves. And when a body is heated, the consequence vibrations on the molecules atomic scales necessarily induced charge oscillation, and assuming that the Maxwell theory of electromagnetic radiation was also valid at the molecular level. So, initially this Maxwell's theory this was checked, it is verified for the bulk materials, big materials, but it is, let us assume that it is good for the molecular level also, and these oscillating charge would radiate, probably giving off the heat and the light absorbed. So, now what is the meaning of this phrase black body? So, this point is actually from that radiation from this heated body depends on some extent on the body being heated. So, it depends on that the material of that body, and for a shiny metallic surface we have different types of objects like metallic objects and some black objects, some glass type objects. So, for a shiny metallic objects the light is not absorbed, either it gets reflected. We know that the reflection phenomena occurs there. For a black material, light and heats are almost completely absorbed and the material gets warm. And how can we understand this different behavior of this type of objects in terms of light as that electromagnetic waves interacting with charges in the material. So, we know that the atoms and molecules of that material we are considering, these are the complex structure with electrons and the nucleus, and that interaction of these electromagnetic waves and with this with these electrons, this actually take part to explain this behavior. So, reflection of light by a metal surface. A piece of metal has electron free to move through the entire solid. It conducts both electricity and heat, and those free electrons they driven into a large oscillation by the electrical field of incoming light waves, and this induced oscillating current radiates electromagnetically. So, actually this that interaction of that electromagnetic waves, that electric field of that electromagnetic waves with that electrons and that mean free path, this actually controls the behavior of this reflection and absorption etc. For a shiny metal surface, the little of the incoming radiant energy is absorbed at heat and it just irradiated, that is known as reflection, reflected. So, let us consider a substance that absorbs light, no transmission, no reflection. So, we come very close to perfect absorption with soot. Like a metal, it will conduct an electric current, but nowhere near as efficiently. There are unattached electrons which can move through the whole solid, but they constantly bump into the things. They have a short mean free path. So, that mean free path is controlling here, and they bump, they cause vibration like balls and hitting bumpers in the pinball machine. So, they give its kinetic energy into heat. So, we can relate this absorption and emission. So, we can see we have seen that the soot can absorb radiation and transfer the energy into heat, but what about the reverse? Why does it radiates when heated? The pinball machine analog is this is still good. Imagine now a pinball machine where the barriers etc. vibrates vigorously because they are being fed energy. The balls here, that the electrons bouncing off them will suddenly accelerated at each collision, and this acceleration changes into electromagnetic waves. So, the electrons in the metal have very long mean free path. So, we can say, and that lattice vibration affects them much less. So, they are less effective in gathering and radiating away heat energy. It is evident from consideration like this that good absorption of radiants are also good emitter. In fact, we can be much more precise. A body emits a radiation at the given temperature and frequency as exactly as well as it absorbs the same radiation, and this is actually proved by Kirchhoff, and we know that Kirchhoff's law in our school level physics. So, now the term black body. So, this any body at any temperature above absolute 0 will radiate to some extent the intensity and the frequency distribution of radiation depending on the detailed structure of the body. To begin analyzing heat radiation, we need to be specific about the body doing the radiating, and the simplest possible case in the idealizing body, which is a perfect absorber and therefore also a perfect emitter. This is called a black body. So, in the simple word, the term black body, this was first time coined by Gustav R. Kirchhoff in 1862, and simply a black body is an object that absorbs all of the radiation, that is receives, that is does not reflect of any light, and nor does it allows any light to pass through it and out the other side, and the energy that the black body absorbs heat is up, and then it will emits its own radiation. The only parameter this determines how much light the black body gives off, and at what wavelength, it is the temperature. And there is no object ideally that is a perfect black body, but many objects like including stars we have approximately like black bodies, and some common examples are filament in the condensed bulb or burner elements on the electric stove. At the setting on the stove increase from low to high, we can observe it produces black body radiation. The elements will go from nearly black to glowing red hot. So, we know from the earlier lecture and just during that background part of this lecture also, when charged particles are isolated, they creates electromagnetic radiation, and that is known as light. And since some of these particles within objects are charged, any objects with the temperature above absolute 0 will contain moving charge particles. So, it will emit light, and the black body, which is an ideal or perfect emitter, emits a spectrum of light with the some more properties like this. So, the properties are: the hotter the black body, the more light is gives off at the wavelength, and that is if we compare two black bodies regardless of what wavelength of light we observe, the hotter will give off more light than the cooler one. The spectrum of a black body is a continuous, and it has a peak at a specific wavelength, and the peak of the black body curve is a spectrum moves to shorter wavelength for hotter objects. And if we think in terms of visible light, the hotter the black body, the blur the wavelength of its peak emission. So, this is the two dimensional picture of a spectrum of black body with different temperature. And now, just coming to the next point, that is from that black body to black body spectrum, and that the diagram earlier I have shown, that was actually the picture of that black body spectrum. So, now do we construct a perfect absorber, because that black body must be a perfect absorber. So, the construction part should be take care of. So, in 1859 Kirchhoffs have a good idea. A small hole in the side of a large box is an extent absorber. What actually happens here? Since any radiation that goes into the hole bounce around inside, a lot getting absorbed on the each bounce and has little chance of even getting out. So, that is a good perfect absorber, and the Kirchhoffs challenges researchers to figure out and measure the energy or the frequency curve for this. This is cavity radiation. So, that radiation actually this is in form of a cavity, that is structure of that big box with that hole, it can be considered as cavity. So, this radiation is known as cavity radiation. So, that Kirchhoffs challenges researchers to calculate that the spectrum of this energy, that radiation with frequency, and in fact, this was Kirchhoffs challenge in 1859 that led directly to quantum theory 40 years later. So, summaries of that properties of perfect black body at a glance. So, to be able to call a body a perfect black body, it needs to possess the following properties: it absorbs all the incident radiation in respective of wavelength and frequency range. There would be no radiation reflected or transmitted. An object which is a good absorber will always be a good emitter. Therefore, a perfect black body will always be a good emitter. So, in reality, there is no perfect black body in nature. So, that is just that structure we have drawn, and some experimental facts about that spectrum. So, that black body spectrum depends only on the temperature, not on the material of the body or object, that is spectrum. At the temperature of the object increases, black body radiation will also increase, and the peak wavelength of the black body spectrums becomes shorter as an object temperature rises. Blue stars are hotter than red stars, and blue stars has the highest peak at 400 nanometer, and red stars has the lowest peak at 700 nanometer. So, we can have that visible range spectrum. Now, some examples of this black body radiation also I have mentioned earlier that one of the good example, that is that light bulb and heating element of that our toaster, solar radiations, cooling of the earth at night. So, these are that good example of black body radiation. And some factors affecting this black body radiation, and these are only two. One is that temperature. As the temperature increases, black body radiation increases, and emissivity, as the emissivity increases, black body radiation increases. Now, the types of black body radiation. So, this black body radiation actually classified on the basis of that temperature range. So, at that low temperature, so on the basis of that we can classify this in basically in three parts. At the low temperature range, that temperature range is given from -40 degree centigrade to 150 degree centigrade, and then extended data black body, and that is high temperature extended, and this is from ambient temperature to 160 degree centigrade, and this area black high temperature cavity black body, this is the ambient temperature, it is the temperature range is from this ambient temperature to 1200 degree centigrade. So, now these are that observation we have observed in that figure, that variation of that emissivity, that radiation with that frequency, and some people tried to explain that behavior, that variation with the temperature, and there are certain laws listed in listed herewith. So, the first one is that Stephen's law, and that is given in the year 1879, and according to this law, the total power P radiated from 1 square meter of black surface at a temperature T, it goes as the fourth power of absolute temperature. So, here if we represent this P as the power and T is the temperature. So, we can say this P is directly proportional to T to the power 4, and if we take that proportionality constant as a sigma, then this P is equivalent to sigma T to the power 4, where this sigma, this represent a constant, and which is known as proportionality constant, and this is known as Stefan-Boltzmann constant in physics, and the value of this constant sigma is equivalent to 5.67 into 10 to the power minus 8 watt per square meter per Kelvin to the power 4. And 5 years later, in 1884, Boltzmann derived this T to the power 4 behavior from theory. So, this is Stephen's law, and this tries to explain that variation with that total power with temperature. And the continuation. So, this radiation shows that when you double the temperature of a black body, the energy it emits per centimeter square goes up by 2 to the power 4, that is equivalent to 16. Means a black body that is 500 Kelvin emits 16 times more energy per unit area than one that is 2500 Kelvin. So, if we have two black body, and one the temperature of first one is 2500 and the second one is 5000 Kelvin. So, since that the temperature is doubled, so that the power will be 16 times, and the total luminosity of the black body, that is how much energy the entire object give up, is the energy per unit area, and this is multiplied by the surface area. And especially if we consider one sphere, then that will be this luminosity L, that is equivalent to 4 pi r square sigma T to the power 4, where L is the luminosity and r is that radius of that sphere. So, that this sigma T to the power 4, it is related to directly that Stephen's law, and that the surface area is taken here is in multiplication. So, this gives that luminosity. Now, the second law, that is these two, the second one is that Wien's displacement law, and it is given in by Wiens in 1893, and as the oven temperature varies, so does the frequency at which the emitted radiation is most intense. in fact that the frequency is directly proportional to the absolute temperature. In some literature this is also given in terms of wavelength. So, this if this frequency is directly proportional to temperature, then there that wavelength will be inversely proportional to temperature, because we know that this frequency and wavelength are inversely related. So, that F maxima, it is directly proportional to T, and Wien himself deduced this law theoretically in 1893, and this is following Boltzmann's thermodynamical reasoning. So, he has adopted that method given by Boltzmann, and this relation was derived by Wien. So, in fact, this upward shift in F max with temperature. So, from the curve we can get this this observation. So, this upward shift in F max with temperature is familiar to everyone. When an iron is heated, the first visible radiation, that is about at about 900 Kelvin, is deep red, and the lowest frequency visible range. And the further increases in the temperature, this causes the colors to change to orange, then yellow, and finally blue at very high temperature, and that temperature will be about 10,000 Kelvin or more, for which the peak in radiation intensity has moved beyond the visible into the ultraviolet region. So, this shift in the frequency at which this radiant power is maximum is very important for harnessing solar energy, such as in greenhouse, and for sun especially this lambda maximum, this can be calculated as equivalent to 0.29 cm Kelvin upon 5800 Kelvin. So, this 5800 Kelvin, this is in general we take that the average temperature of this sunlight which is coming from that photosphere of that sun. So, after calculation it is equivalent to 5 into 10⁻⁵ centimeter, and further one can convert this in nanometer, and that is equivalent to 500 nanometer. Now, the final explanation by Planck's law of radiation, and the first successful theoretical analysis of data, that was by Max Carl Ernst Ludwig Planck in 1900. As we have mentioned here earlier that this is actually given in 14 December 1900, when Planck postulated this theory to explain the behavior of electromagnetic wave, that light wave. And this Planck's quantum theory, this has following presuppositions. The first one is the discrete packets or bundle of energy are emitted or absorbed intermittently, it is absorbed by the matter. So, initially that energy of that light which is considered by that Planck, it is not the continuous one, it is actually in the discrete nature, means where we have that discrete stepping like nature. So, that quantum is the name given to the smallest bundle of packets of energy, and using light as an example, a photon is a quantum of light. So, the terms quantum, the terms photon, although the term photon, this was given this name about more than 25 years later, the first name, that was the quanta given by Planck. So, here the absorbed energy, quantum energy, it is proportional to the radiation frequency. So, that we have observed that energy, it is proportional to the frequency, and we have this relation that E is equivalent to h nu, where this h is known as Planck constant, and I have also mentioned earlier this Planck constant, this was measured by different experimentalists, and its value is actually equal to 6.626 into 10⁻34 joule second, and nu, this is the frequency of radiation. And by using this Planck's law, a black body's emitted radiation may be termed by its frequency variation, and the Planck's radiation, a form of thermal radiation, is another name for this type of radiation. So, earlier we have proved that this photon has wave nature as well as this particle nature. So, for that heating effect, earlier we have mentioned in the mechanism that heating effect is because of that interaction of that electromagnetic wave or the interaction of that electromagnetic wave with that atoms or molecules of that substance. So, that interaction, so here according to this Planck's hypothesis, we can say this is actually the collision between that the photons with that the particles or that atoms or molecules of that system. So, that collision can generate the heating effect or that radiation. So, not only that radiation or also the thermal radiation, it is occurred due to the incident of that photonic energy on that surface. And the greater the temperature of the body, the more radiation of a wavelength is emitted by it. This is that statement given by Max Planck. And also this one term, that is the quantization, is coined by earlier it was coined by Niels Bohr, that the momentum is quantized, but it is taken by this Max Planck also, that it is that the energy of this light, it is also quantized. So, here that initial energy, that E is equivalent to h nu, it can be rewritten as E is equivalent to n h nu, where n is equivalent to 1, 2, 3. So, it is integer multiple of h nu, that h nu is that smallest energy value. And he has then calculated one formula for that black body radiation, or especially that radiation, and which is known as Planck's radiation formula. And that method of calculation, that was that phenomenological simple method. For the simple method, how that, since this energy of this photon is quantized, which we are taking this E is equivalent to n h nu. So, that energy of that photons will be equivalent to h nu, 2 h nu, 3 h nu, 4 h nu, and so on up to n h nu. So, the method of calculation was actually equivalent to simply he has collected that simple, that phenomenological method, he has collected that the total amount of energy, for example, in a bucket, and then he has separated out in the group of photons, one group of photons, that is the total individual energy of each photons, that is equivalent to h nu. Second group of photons, collecting photons, that is the energy of each photons is equivalent to 2 h nu, and then the third group of that photons, that is that 3 h nu, and say on it up to that n h nu. Then the next step will be the total number of photons having energy h nu, that was calculated, and the second the total energy of that photons of that energy 2 h nu each, that is separately calculated, and then the third one it is calculated, and further the calculation is performed, and then the complete adding process is there, and then we have this some mathematics like the series calculation of all these things, and after adding all these terms, one get that final formula, which is known as Planck's radiation formula. Although that I have just given that the mechanism Planck had tried, but that calculation is a little bit difficult. So, that derivation is not given here. So, by adding that, the final formula obtained by that Max Carl Ernst Ludwig Planck, which is further known as Planck's radiation, and the formula for that in the frequency range nu to delta nu, nu to nu plus delta nu. So, that is equivalent to u nu du nu, that is equivalent to h by h. So, sorry. So, that Planck's radiation formula that was obtained by Max Planck, it is u nu del nu, that is equivalent to 8 pi h nu cube by c cube delta nu, and that exponential of h nu by k t minus 1, and here that h nu by k t, this h nu is equivalent to the energy of that photon, and k is Boltzmann constant, which is equivalent to 1.38 into 10 to the minus 23 Joule Kelvin. So, this actually correlate with that the kinetic energy of that system with the temperature terms, and that denominator of that equation, it is somewhat related to Maxwell's Boltzmann's distribution function. So, this is that final formula for that, and the perfect agreement of this formula with the precise experiments and the consequence necessary for the that energy quantization, and this was the most important advance in the physics in the century. The physics, although that all the experimental observations related to that radiation with the frequency, that was the beginning in between that 19th century, and the explanation, the final explanation of that black body radiation, that was given by Max Planck in the beginning of that 20th century, and that was that the great explanation which actually the turning point in the quantum physics, and that classical theory that was earlier failed, and this is the one method to explain that. Now, the application of that black body radiation. So, black body are used in the following places. So, for first one is that thermal imaging, second the calibrating and testing the radiation thermometer, lighting, heating and security, and some optical sensors. That black body radiation is very much useful in the optical sensor, and nowadays this is a very nice technology, people are interested on this. So, as a summary, we can have the black body is an ideal surface or body that completely absorb and re-emits all of the radiation that falls on it without reflection. Second, that electromagnetic radiation emits by any heated object is called black body radiation, or this is also known as cavity radiation, because in practice there is no perfect black body. So, that cavity is created to mimic this black body radiation. And one of the characteristic features of this black body radiation is the continuous frequency spectrum, that is only depends on the body temperature, and it is called the black body spectrum. And we also studied the classification of this black body radiation based on temperature variation. We have classified into 3 to 4 parts, and then we have Planck's law, Wien's displacement law, and Stefan's Boltzmann law. To these are that 3 laws of radiation that actually explains this black body radiation in consequences in the sequence, not a complete theory, that is that was that initial theory and final theory of that Planck's theory.